Okay, so our final topic in mechanics of materials are failure theories. So failure theories, basically what it is, failure occurs when the stress, the internal stress of a material reaches a critical point where it starts to propagate any existing defects, not necessarily dislocations or grain boundaries, but existing cracks, for example, or vacancies within the material can start to propagate and then create fracture that would ultimately lead to failure or yield. So a set of criteria must first be developed to evaluate the stress state of a material against a uniaxial test. So what I mean by that is a uniaxial test is used to compare against the criteria we're about to develop in failure theories. And why we compare against a uniaxial test? Well, we don't really want to compare it to a biaxial or even worse than that, because that requires more time, it's more costly. Uniaxial tests are essentially cheaper and easier to measure. So we need to compare our state to what we find from uniaxial testing. For different materials, there are different types of criterions. For example, composites like carbon fiber or fiberglass have their own set of failure criteria. We won't cover those. We're only going to cover the isotropic materials for today. And we're really going to cover two versions of isotropic materials. The first being a brittle material. It yields because the brittle material typically has the crystalline structure of a brittle material is more porous. It's more spacious. There's more distance between the atomic particles within a brittle material than there is with a ductile material. And typically, the stiffness of brittle material, if we look at the stress strain curve here, and we go here, let's say this is a ductile material, and then it would have some yield curve like this. Brittle material would typically be more stiffer here. So and another thing to note is that brittle material don't yield. So there are different failure criteria. There's the yield and there's the ultimate failure. Obviously, ultimate failure occurs when the state of a material reaches a stress point. It basically fractures. There's no more internal stress since it's starting to separate. So we call this point right here ultimate failure. Ultimate failure for brittle material doesn't go into a parabolic curve nicely like ductile materials do. It just fails. It just cracks instantly, which is sometimes when you analyze a brittle material or you do a uniaxial test with a brittle material, there's just going to be an instant pop or a snap sound you'll hear. So brittle materials, ultimate failure, there's no yield, and brittle materials don't change in geometry or distortion when you go past the yield strength here. So that's really the difference between ultimate, which is stress ultimate here. And we'll say this part is stress yield here. If everybody remembers where the yield stress is, the yield stress, you basically have to take a point that is 0.02% strain. Oh, I'm sorry. It's 0.2% strain. We take a line from that point on the strain curve and we draw it parallel to the stiffness, parallel to the elastic line here until it crosses over the, let's see, let's draw this a little better. It crosses over the stress strain curve here. And that's typically what we pinpoint as the yield strength of a material. So that's essentially the difference. It starts to plastically deform after yield. So moving on to ductile materials. Ductile materials yield due to movement of grain boundaries and dislocations, like I just said. What happens atomistically here, let me just draw it. What happens atomistically here is if we have this cartoon drawing of a pair of atoms or metallic atoms that are bonded together, metallically bonded in a material. Let's assume this is something like steel or aluminum, and we apply a shear stress here, right? What essentially happens here, the shear stress is going to move the atoms. This atom right here does not want to get pulled over because it's attracted to this guy right here, but this atom is assisting with the push to the next equilibrium position. And what essentially happens, there comes a time where the pull from this guy becomes overwhelmed by the applied shear stress, and the pull from this guy overwhelms the push from this guy and the shear stress from here. We essentially get a new formed crystalline structure of equilibrium, which is what we define as plasticity, okay? So that's essentially what this last bullet point means. So ductile materials yield due to movement of grain boundaries dislocations. All right, so now we're going to go ahead and go into the actual failure theories themselves. So we're just going to start off with brittle materials. And brittle materials, this is essentially straightforward. Isotropic materials. The primary failure criteria we use is called Ranking's maximum stress failure criteria. So Ranking's maximum stress failure criteria means that whatever, and this is for normal stresses, whatever normal stress reaches its maximum capacity, it fails when it equals the ultimate stress of a brittle material. Again, a brittle material typically does not have yield, it just has ultimate or fracture stress. So if you look at a principal axis for, say, principal axis 2, so for a 2D element, if we look at the principal axis for principal stresses of 1 and 2 direction here, what that would typically mean is that if the 2 or the 1 direction experiences sigma alt here, the material fractures. Now, typically with this theory here, we assume that sigma alt is also the same for compression. There are adaptations to this where sigma alt for compression could be different. So, and this is a negative here. So these guys will consider tension, these guys will consider compression, and typically the failure envelope we draw is a square or a rectangle if you're also considering a special case with compression. Okay, so essentially what that means is that in a 2D case, if your principal stresses lie outside of this failure envelope, your part's going to fail. So that's how to look at it graphically. Now, how to look at it using analytical methods, the first thing we do is we establish failure criteria for ranking. So I'm going to say if the ultimate compressive strength here, so they'll give it to you, they'll document it, ultimate compression strength without the negative. We just put the negative here for completeness of relating literature to documentary. Failure won't occur, or the criteria of failure won't occur if your principal material direction is between the ultimate compressive strength and then the ultimate tensile strength. Ultimate tensile strength being positive because it's tension for nomenclature. So essentially that persists for the other two normal stresses. Okay, so the maximum normal stresses are the principal directions, and when we find the principal, when we find the principal stresses, there are no shear stresses that are considered, so it's only just these guys. And yeah, our criteria must lie within the boundaries of ultimate and tensile strength here. So just to be complete, for the sake of analysis, if the principal stress here is in tension, which I'll denote as positive here, you would use, or you would compare it to, so which ultimate stress do we compare it to? You would compare it to the tensile strain. Pretty straightforward for why that is. So again, if negative, you would use the ultimate compressive strength here. Okay. If the ultimate compressive strength is not given, all right, if that is not given, assume that the ultimate tensile strength is equal to the ultimate compressive strength. Okay. And that's really it for the criteria. Now for the safety factor, right? So how do we determine, using a quantifiable number, how do we determine if the material fails? Because it's easier to understand via numbers. So safety factor, which I'll denote as capital N. Safety factor for ranking is basically the minimum value of if you compared the each principal's stresses to their respective ultimate stress. Okay, so we determined that using safety factor. Now, people in industry might not be familiar with safety factor. They use something else. It's called margin of safety. For safety factor, by the way, if the number you get is less than 1, that's basically failure. Okay, margin of safety is basically the same thing as safety factor. Safety, where it's basically the safety factor n minus 1. So in this case, right, if n is less than 1, then this will come out as a negative. So the margin of safety is a negative number. If n is greater than 1, then it would be a positive number. So people in the industry use positive or negative numbers to determine whether the material fails or not. So that's essentially what margin of safety is compared to safety factor. And that's it for brittle materials. So the next thing we're going to move on to. So the next and last thing we're going to move on to are ductile materials. Again, it's all isotropic. Okay, so the failure criteria we're going to look at first is the more popular of the two methods I'm about to show you. It's called Trescas max shear failure. Now, Tresca has another reasoning for this, but essentially, if you observe physically, if you've seen uniaxial test with an aluminum specimen, you'll typically see that the failure occurs at some degree close to 45 degrees, right? If you guys remember from our Morse circle, from the principal stresses, so you would assume the principal stresses be uniaxial and transverse of the test specimen, that our maximum shear occurs at this angle right here. That would be 90 degrees. Now, if you remember, what occurs in Mohr's circle is basically 2 times more what the principal orientation, or 2 times more the orientation difference we have for an actual specimen. So this would translate to 45 degrees in the physical problem here. So that's basically the idea. We assume that shear stress is the reason why ductile materials fail, like aluminum or steel. So essentially, we find our tau max, and I'm going to rewrite this because I think I wrote this earlier. Absolute value of sigma 1 minus sigma 3. For completeness sake, if this is a 3D model, it would be sigma 1 minus sigma 3, sigma 3 being the smallest principal stress, sigma 1 being the highest. For a 2D case, this would be sigma 2. Divided by 2, or, like I just said, tau max for 2D would be sigma 1 minus sigma 2 over 2, essentially. Okay, so that's straightforward. So the failure criteria, so many people have different criteria for yield. They either consider it, or different criteria of failure. They either consider it the yield strength or the ultimate strength. We're going to use what typically people want to analyze. It's yield strength. They want the material to remain in the elastic region. They don't want it to plastically deform. So if the material plastically deforms, we assume it just fails. So we'll assume that the failure criteria is yield strength. And the safety factor here is equal to tau max divided by yield. Okay? And that's essentially that for Tresca. Now we move on to the last failure criteria here, which is von Mises, or this would be also known as maximum distortion energy criteria. Okay, so I'm not going to get into the details of maximum distortion energy derivation. All you essentially need to know is there are 2 types of forms of energy, or rather, there are 2 primary ways a material experiences stress and deforms based off that stress. There's one way which is known as uh, bulk or volumetric stress. Think of hydrostatic pressure, the feeling of when you're deep underneath water, or when a material is deep underneath water, it experiences equivalent bulk stress all in all 3 primary directions, right? So that's one way. Another way is if you put a non-uniform stress on a material, it will distort as such. So this would be due to a combination of shear and normal stresses that are not equal in magnitude to one another. So essentially what that means is the strain energy density, or the total strain, not the strain energy density, the total strain of a material would be that distortional energy plus that volumetric energy that we input into a system here. So if you go ahead and rearrange this for a 2D case, go ahead and rearrange this so we only have the distortion energy on the left-hand side here. This would be the total energy subtracted by the volumetric energy here. And for a 2D case, that would be 1/6 times the shear modulus times sigma 1 squared plus sigma 2 squared minus sigma 1 times sigma 2. Okay, and that's that for that case. So in a 2D case here, we need to now compare this to a uniaxial test. So for a uniaxial test there, the sigma 2s would disappear. So So for general static case here, which is the equation above, it would equal that from a uniaxial test. Okay, that whole thing would be written out as 1 over 6 times the shear modulus principal stress 1 plus principal stress 2 squared minus sigma 1 times sigma 2, both equaling 1 over 6 shear modulus here. And then it would just be yield. For the uniaxial test, it would be yield squared. This goes to 0 and this goes to 0. Okay. Essentially, what that outputs us is the following criteria must be met for failure to occur or not occur. The equation here on the left-hand side, now the 6 times shear modulus basically cancels out one another, minus principal direction 1, principal direction 2 here. That whole equation right here must be greater than, or if it fails, it equals to the yield strength squared. Okay, so that's essentially the criteria to determine maximum distortion energy failure for a ductile material. Now, how we determine the safety factor from this? So for this criteria to meet the failure, this left side must equal the right-hand side. And the only way this left-hand side can equal the right-hand side is if there was a multiple safety factor here. We're going to go ahead and call that lambda. There was a multiple safety factor here that gets carried out between these values that would equal the failure stress here. Okay, so that multiple lambda would not be just multiplied out against each existing principal stress here. What we would do here is we would accompany each principal stress with that multiplier, lambda multiplier here. Lambda, by the way, is our safety factor. So if you imagine lambda would be some value that would make sigma 1 and sigma 2 equal sigma y squared. That's essentially the whole philosophy. Whoops, I wrote this wrong. Minus lambda squared, because it would come from sigma 1 and sigma 2. Sigma 1, sigma 2 would equal sigma y squared. Okay, so if you go ahead and move everything to the right hand side but just keep lambda on this side, you'll end up with the safety factor for von Mises 2D criteria would be the yield strength divided by square root sigma 1 squared minus sigma 2 squared, I'm sorry, plus sigma 2 squared minus sigma 1 times sigma 2. Okay? And that is the failure criteria for von Mises. Now for a 3D case, 3D von Mises, the equation would be written out as principal stress direction 1 squared plus principal stress 2 squared, and then principal stress 3 squared minus each one of them is a multiple of each other. Uh, 2 minus sigma 2 sigma 3 here, and this again must be greater than or equal to sigma yield squared for the same exact reasons. And if you did you follow the same procedure I did here, you'll essentially get lambda equaling everything here on the left-hand side underneath and square root of this, the denominator of sigma yield, okay? And that's essentially it. So now we're pretty much done with everything for mechanics of materials. And if you guys have any questions, go ahead and shoot me an email or contact me. You know where my office hours are.